Thank you. OK, I hear myself. We're good. OK. So hi, I would like to thank you guys all for coming, and specifically to this talk on Apache Spark on Kubernetes and HDFS Security. Just as a brief introduction, my name is Ilan Filonenko, and I'm a software engineer at Bloomberg. Bloomberg and several other companies have been building a new big data stack on Kubernetes, and together we made it possible to run Spark on Kubernetes. Now, as we are adding HDFS, which is Hadoop distributed file system, to the big data stack, we want to make sure that Spark and HDFS work really closely and really well together. And it did present a few problems in the beginning when we introduced this to Kubernetes. So that's what I'm going to talk about today. OK, so here's the outline of the talk. First, I'll do a quick introduction on what is Kubernetes. Then I'll talk about how we are building the big data stack on Kubernetes. And then I'm going to give a short demo on how to run Spark on Kubernetes with a deep dive into secure HDFS support. And then I'm going to come back and then talk about how we run HDFS itself on Kubernetes and do a deep dive on the data locality features. But first, what is Kubernetes? So Kubernetes is a new open source cluster manager software. I guess not that new. It's 2014. So it manages many computers and runs many programs using those computers. In some sense, you can think of it as similar to Yarn and Mesos. So what sets Kubernetes apart is that when it runs programs, it puts them in special runtime environments called Linux containers, which are also known as Dockers or Rockets. Now, these containers and Dockers are really popular, and people want to run them on a cluster. And this is where Kubernetes comes in. And it was actually designed and built for containers based on Google's experience of running containers for 10 years. And ever since it was released, as you can see, there's a lot of contributors, and they built quite a big community around it. So what is the benefit of using containers? So many of us have had this bad experience of my Spark job suddenly fails with a class not found exception when someone installed a new version of Spark. Or you have to change your Tomcat port because someone else is running another version of Tomcat with that same host. Now, they shouldn't be able to affect your work. So containers solve this problem fundamentally. What they do is they create more isolation layers between programs using virtualization technologies that virtual machines are based on. But unlike virtual machines, containers are really fast because they pick the specific set of technologies that are efficient and very lightweight. So first, each program gets a virtual file system that contains an independent set of software packages. So one person can install new packages on his container without affecting your packages, which is commonly referred to as a Docker image. And these Docker images are hosted in a Docker registry, which I assume most of you guys are aware of. So what if I have a server program like Tomcat? Do I need to change the port depending on who else is running Tomcat? Now, Kubernetes gives each program a virtual network interface that comes with a unique virtual IP address. And so both your Tomcat and my Tomcat can both be open on the same port under different IP addresses. So there are also more isolation layers, such as process ID spaces. This allows for users to not kill your personal processes. Also max memory limits and CPU limits. Now, you can also mount external data on containers using volumes, and also you can use credentials, such as Kubernetes secrets and local disk directories using stuff like host path. With these virtualization technologies, Kubernetes became very popular in the realm of microservices, which are pretty much simple service programs that only allow one service. So here's how a Kubernetes cluster looks. You have multiple cluster nodes like node A and B. Now, there can be more nodes, but I'm only showing you two. And across the cluster nodes, we can run multiple programs in these things called pods. But what is a pod? So a pod is a unit of scheduling and isolation in Kubernetes. And a pod typically consists of two containers. It runs a user container like Tomcat in a primary container, and there's also an infrastructure container that holds isolation layers like a virtual IP address. So here you see pod 1, 2, and 3, and each pod may have a different Docker image. Now, each pod has a unique virtual IP address, like, for example, in that image it's 10.002 or 10.003. But because these are virtual, these pod IP addresses will look different from the physical node IP addresses, like 196.005. So we found that at Bloomberg, we wanted to run multiple big data applications on top of Kubernetes, one of which was Apache Spark. And it was exciting to see that we were not alone in this endeavor. So as such, Bloomberg began working with various companies on building native integration for Kubernetes with Apache Spark in a fork before it went upstream. So just some advantages for people who are still not using Kubernetes in the workloads, but they're trying to use it in Spark standalone. There's a lot of benefits in native integration, one of which is that Spark executors can be elastic depending on job demands, as they can communicate directly with the Kubernetes client. You're also able to leverage Kubernetes contracts like resource quota and service accounts. You also have greater resource isolation and security. And you also allow the user to specify a Docker image when he submits a job for the driver and the executors. Now, we're excited to say that Kubernetes is a part of Spark 2.3, and since then have a lot of features that we've supported in 2.4 and moving forward. So some of the features in 2.4 to look for is that non-GFM binding support specifically and memory customization. So this includes support for Python 2 and 3 in their Docker images, specifically for PySpark applications, Spark R, and the ability to customize the memory overhead factor, as well as executor PySpark memory based on Python address space limits like R-limit. We also allow for client mode support for running interactive applications and notebooks. And we also had a very large refactoring of the code base, which led to the removal of the init container, as well as more structural changes that are quite large. And so, for example, one application is that with the removal of the init container, the driver pod no longer uses that to download remote dependencies, such as files or jars that you might get from like HTTP servers, AWS, HDFS, or S3. So instead, the driver now uses Spark submit in client mode, which automatically fetches these remote dependencies in a Spark idiomatic way. Now, this has resulted in these files going into like var spark data/spark files, which means that you have to run sparkfiles.get in your Spark application, which is very idiomatic of how you usually do it. But this has led to issues such as not being able to do --by files or being able to resolve your file locations internally. And so some solutions that are now being presented is that there's feature work on allowing for a pod template spec, which allows for you to actually define predefined volumes using like config maps, and then you can actually put those in, thereby allowing for you to do local application dependencies. But moving forward, we will have a research staging server, which allows for you to do that kind of work. Other features that were added was the management of executor pods is now using a level trigger mechanism. And future work will also include dynamic resource allocation and a shuffle service, and support for Kerberos authentication, which is going to be talked about in this talk, and it's linked down there, which hopefully should be merged. So, but how does a Spark job launch using resources managed by Kubernetes? So to do this, we modify the Spark core to allow for it to communicate with the Kubernetes scheduler backend. And this scheduler backend contains all calls to communicate with a Kubernetes cluster, such as resource requests or authentication. But how do you launch a job, right? So you would submit a job from outside the cluster, for example, and then the driver launches in a pod that will be configured using a submission client. And the driver, in turn, will launch executors in the pod across cluster nodes. And the driver and executor pods will also get unique virtual IP addresses that they will communicate with. And this communication, as I said earlier, happens via the virtual network interface. Now, if other jobs, for example, run within the Kubernetes namespace, or in the same one, so namespace is a virtual cluster backed by the same physical cluster, they'll not interfere with each other because they're all unique pods with possibly unique Docker images. So how do you store big data that Spark needs to access? So some solutions are S3, but more commonly to store in HDFS. Now, there are two options for that. HDFS running outside the cluster, in essence a remote DMZ cluster that Spark and Kubernetes can communicate with. Now, as HDFS in production clusters is commonly secured with Kerberos, these Kerberos clusters will therefore have 3 unique nodes. So the first is a Kerberos node, which functions as an authentication server for users and services, also like a KDC node is sometimes referred to. Now, since HDFS also has a master-slave architecture, the other 2 types of nodes includes a name node, which is like a master server that manages the file system namespace and also regulates files and there's access to the clients, and data nodes, which actually manage storage attached to the nodes that they run on. These data nodes have the ability to perform block creation, deletion, replication upon instruction from the name node. Now, as you can see from the example, the name node and data node live outside of the Kubernetes cluster or that namespace, and so as such, the other option is HDFS running on Kubernetes itself by loading the name node and data node as pods with unique labels and mounts that we will elaborate upon later in the talk. Now, these Helm charts, which were created by Keymoon from Pepperdata, still exist in our fork, but we are currently creating an HDFS operator to work in tandem with the Spark operator. So I'll now do a short demo elaborating on how Spark and Kubernetes interact to secure HDFS, and then dive a little deeper on how this actually interaction works. So I'm clicking the third link, but it's over here just for the sake of making it easier, because demos. So we're going to begin. Does anyone see this, by the way? Right? We're good? OK. So in the beginning, as we're checking what pods actually exist on our current namespace, we see that we have the data node, the KDC node, and the name node that I described earlier. So we're simulating a single-noded pseudo-distributed Kerberos cluster. Yeah, you guys can't see it? OK, we'll do it this way. See how that works out. And so what we're going to do now is we're going to deploy a little sandbox environment to actually run an example Spark submit command. So I'm going to exec into this environment, and that's a sleep pod, but it has a key tab that I can leverage. And so what we're going to do is we're actually going to look at the example Spark submit command. So this example command has the Hadoop config directory defined as a environmental variable, as you can see over here. And then we also have the Spark submit command, which has the uniqueness of having this master defined with the K8S endpoint. But other than that, all you're specifying is the key tab and the principal, as well as the location of your KRB5 file. Now this key tab and principal has become now generic for all cases like Yarn and Meso, so it all has the same config value. And after we continue running it, we're now going to execute it, and then we're going to see how the actual function works. So in the beginning, you see the key tab commit succeeded. And then the system is now running. So this is how the interaction actually works when you're running these kinds of applications on Spark and Kubernetes. And quick thing to note is that the volumes, as you can see, we have the Hadoop secret and the KRB5 file mounted on the driver. And it succeeded. And we checked this by looking at the logs, and we see how we can actually see the contents of the HDFS file. We're going to do one more test. And so what we're going to do is we're actually going to not include the key tab, and we're just going to do a K-init. And well, trust me, the results are the exact same, but we'll watch it. But yeah. Okay. So in this deep dive, I'll now begin by explaining what are Kerberos tickets, what are HDFS delegation tokens, and how we're supporting long-running jobs and access control to secrets. Pretty much explaining that whole secure HDFS concept and how we're actually doing that Spark submit. So but first, how does Kerberos actually work and what is it, right? So the goal in secure HDFS interaction is that a user wishes to communicate with a name node to, for example, access a data block that's located on the data node. And the name node is configured and can only be accessed with a unique password called HDFS password, right? So you have a little databases designed with the HDFS password, as you can see. Now, Kerberos, in Kerberos, it should be known that every service needs to have its own account, and there must be a password attached for verification to ensure the user doesn't send sensitive data to malicious services that are unauthorized. And all users and services are registered in the Kerberos server. In this case, it would be user A and service HDFS. So user A will communicate with the server to obtain a session key, or SK1, that will use to encrypt conversation with the HDFS name node to ensure that HDFS isn't malicious and user A is in fact user A. Now, Kerberos server's goal is to give SK1 to the server and the user secretly. Now, in this case, it would be user A and service HDFS. So user A will communicate with the server to obtain SK1, and then what we'll then do is the response message will be sent will be a nested message with 2 copies of the SK1 for both the user and the HDFS name node service, each of which is encrypted with its proper password, either HDFS or user A. So this is in essence like having 2 copies of a receipt, the merchant copy for HDFS and the customer copy for user A. The analogy continues by imagining 2 nested safes, where you put the merchant copy for HDFS into the smaller safe, which we would lock with HDFS's password, and then putting the customer copy for user A into the larger safe and locking that with user A's password. And then what you do is you send the entire safe to user A, and the user A will then unlock that with his password. So then obtain SK1 and send the remaining inner safe over to the HDFS name node to unlock with its unique password to obtain its version of SK1. Now, these SK1s are the same, so what's also important is that the message also includes information about user A, so the server knows which user actually sent that message. Now, the function of this is that user and HDFS may communicate with each other over an encrypted channel using a known session key. Now, having SK1 that is encrypted to HDFS is also known as a HDFS service ticket, showing permission for a user to use the HDFS service by the Kerberos server. Now, tickets are good, but they aren't sufficient for big data applications because there's a security loophole where tickets can be reused. Now, as such, the Hadoop developers allowed for Kerberos tickets to be stamped with client IP addresses to eliminate the possibility of reusability. However, this won't work in a Spark application where there are multiple executors on different cluster nodes. As such, HDFS leverages delegation tokens, which are provided by the name node only, if the client has a valid ticket. Now, but these tickets have no client IP. Sorry, these tokens have no client IPs. So this then allows the drivers and executors to use these tokens for communication with HDFS. However, this token needs to be sent to the driver and executor somehow. And this is a feature that was missing from Spark and Kubernetes, and in essence is the secure HDFS interaction support that I'm talking about today. So Spark on Yarn before 2.3 had an implementation by sending the token to the resource manager daemon that would handle the rest by placing the token directly into the working directory of the driver and executor. Now, we wish to mimic this type of service. However, we obviously don't have Yarn primitives. As such, we leverage Kubernetes secrets to communicate the token to all the driver and executor pods. Now, remember when we talked about namespaces? Well, these secrets are shared across namespaces where all the drivers and executors would have access. Now, these secrets are primitives which are exclusively used for specifically secure like sensitive data, which is hosted via TLS, and that can be used and accessed by privileged pods that wish to mount that volume onto itself. As such, we modify the Spark client to allow for the client to put up the token obtained into the secret. So then first the user will input his password using something like K8S, in essence obtaining a ticket granting ticket, or TGT, that he will communicate to the Kerberos server to obtain an HDFS service ticket. Right, so he obtains a ticket, and then this ticket the client will then send to the name node to obtain an HDFS delegation token that will then mount as a secret for the drivers and executors to then use. However, a delegation token expires after 24 hours, obviously, and a service ticket expires after 7 days. As such, there needed to be a mechanism to ensure that there is a service available that would replace and update the token such that long-running jobs, both above 24 hours or those machine learning jobs that we usually use, could be above 7 days, for example. Now, these would have to run without having to stop because of unprivileged access to a name node. So this is done in Yarn by using the resource manager daemon, but instead we're leveraging the flexibility of Kubernetes and managing microservices to run this as a microservice responsible for updating the token. However, this unique and separate pod will obtain its own HDFS service ticket from Kerberos with its own unique Kerberos system account that have a different privilege than other job user accounts. The uniqueness of this account is that as a generic refresh pod across namespaces, or just a given namespace, there might be other jobs running on that same namespace, so the refresh pod will need to service multiple jobs at once. However, even though the refresh pod uses its own principal to obtain HDFS service ticket, it'll get a delegation token that is, however, stamped with the job user's principal to ensure that the job user only has access to the job user's data. So in essence, as a proxy, it updates the job user's delegation token on behalf of the job user. And then after retrieving a new delegation token, it updates the secret. And then updates the secrets are automatically detected by the pods. And so this simplifies the awareness that drivers and executors need to actually have of this. Now, what's really important to note here is that this specific design is very realistic in enterprise environments where sysadmins might actually not want to give out key tabs, and instead will want to give out less powerful expirable delegation tokens via their own custom renewal or token services. So this is very pluggable in terms of just replacing your own renewal service specifically for however you want to update that secret. As such, they would just populate the secrets, and another option, for example, for Spark Submit is to specify a pre-populated secret, which I'll show in the demo in a little bit. However, what happens when multiple jobs run on a single namespace? So how do they ensure that one job user isn't able to communicate with another job user's data? This problem is solved with access control primitives available in Kubernetes, but becomes pretty tricky once you look at all the options that exist in various organization structures with unique SLAs. As such, we need to restrict access to HDFS delegation tokens and the renewal service key tab stored in these secrets. So the job owner's HDFS delegation token should not be exposed to other users or their jobs. Otherwise, what's going to happen is that they would steal or destroy the job owner's HDFS data. So in essence, this renewal service pod will be helping long-running jobs, and an exception in that it should be able to read or replace the delegation tokens. Now, the renewal service key tab obviously should only be accessible to the sysadmin user or the renewal service pod itself, because if anyone else has it, they have access to destroy HDFS data on many users. So can pretty much Kubernetes authorization mechanisms meet these strict requirements that organizations might have? Well, it depends on which authorization mechanism you use, but in examples, for example, RBAC, or role-based access control. And so Kubernetes RBAC uses roles and rules to represent privilege for accessing Kubernetes resources. But with the uniqueness of every company's organization structure and the SLAs that come with their unique business, they might need to restrict access in unique ways. So given that namespaces are the smallest unit of granularity, we propose that admins restrict access by one of three options. The first option is per user access control, which is manual, in which case you have each user sitting in its own namespace. Now, this might not work in certain situations if you don't want to have a user per namespace and then your name node having all these configurations per user. So the other option is to have a per group access control, which is also manual, in which you have a namespace dedicated to a group of users. Well, let's say you have guys dedicated to financial tickers or whatnot. And then what happened is they all share the same service account, and all the users within the group have access to all the same data. Now, obviously, in most cases, you want to have, for example, in that financial group, you want to have a production and dev kind of granularity in terms of accessibility. In that case, you'd have per subgroup access control, in which you have a namespace with subgroups that have different privilege levels. Now, this can be solved by applying owner labels, for example, to secrets dynamically, meaning that per job that's coming out, you create these secrets that will then destroy based on these owner labels upon completion of the job. However, this still needs to be implemented for Kubernetes RBAC, so it's still not available as an option. However, the other option, and there will be though, but another option is to use an authorization plugin to give specific users access to pre-populated secrets or pre-created secrets. And then obviously, once again, these pre-created secrets can be actually defined in a Spark submit command. And then an example of this I'll show you in this next demo. So we're going to check out all the secrets that exist. And since the last demo, those 2 secrets that were created first via the key tab option. The second option was running using K8S. And the third option, I just created a pre-created secret, storing the delegation token. And then I'm going to try to now leverage it in my Spark submit command. So right now I'm going to describe the secret. I see that the secret has a label saying that whatever refresh pod service that I'm using specifically looks for that label. So as such, that label will then be used to determine I'm going to refresh that secret. And then with the specific item key being there, as such, when I look into my actual command, I'm going to now go back into that sandbox environment. I'm going to look at my Spark submit command. And as you can see here, I'm specifying the secret name and then the item key, because the item key is also versioned. As such, when I submit this, well, it's going to succeed. So yeah, I'm also checking to make sure that there are no credentials stored in the ticket cache to show you that you're actually itself, yes, using just the pre-created secrets. And as you can see, earlier on it says that the TGT is empty and there's no principal. As you can see, we're storing a secret there. And it will succeed in a sec. And it completed, yeah, as expected. Yeah. So that was secure HDFS support. Now let's talk about HDFS running on Kubernetes itself. And this HDFS on Kubernetes will be useful long term in the case that you want to move your data onto Kubernetes so that you can consolidate your infrastructure all in one place. Now, the ability to run HDFS on Kubernetes has shown a lot of traction recently, and as a result is why there's now work on an HDFS operator. So how do you run HDFS, right? So we leverage Kubernetes support for microservices so that you can run HDFS as a collection of microservices. Now, HDFS has 2 types of daemon programs in essence. Similar to the talk earlier in terms of like we're specifying what are the actual like KDC nodes, name nodes, and data nodes. So the name node daemon maintains the file system metadata. And we support the name node by using HA, so we have 2 instances of it. So if one person accidentally turns off the power on node A, Kubernetes will automatically start a replacement name node on a different cluster node, say node C, and remount the persistent volume of 1 on the name node. And we want to make sure that this is then spread across 2 specific pods across different cluster nodes. And this is done via a stateful set of size 2, meaning that there should always be 2 pods running at a given time. Now, to make sure that it's 2 pods running on different cluster nodes at all times, you use the Kubernetes API anti-pod affinity. And what this allows you to do is that you want to say that I don't want my pods to go near each other, especially not on the same cluster node. So if you have 2 name nodes, but only one name node should be active at a given time point, to determine who's active and who's standby, you use something like Zookeeper, which is pretty much a way for them to determine their own HA setup. And their HA setup is also set up so that it's a stateful set of size 3. Now, I didn't show it here, but they also have their own persistent volume, which is what pretty much their data is based on. Now, the second HDFS, and once again, the active name node should then modify the metadata as clients make requests for adding or deleting files. And the metadata updates will be then shared with the standby node. And this can be done via a helper service called journal nodes. And they're also done in a stateful set of size 3. This is an example Helm chart, for example. That's in the link above. And so the second HDFS daemon type is a data node, and that stores the actual file data. Now we run 1 data node on each and every cluster node, which is a rule enforced automatically by another Kubernetes construct called a daemon set. And this rule applies even in the future, in which case if a cluster admin, for example, adds 10 more cluster nodes like tomorrow, then each of them will start 1 data node pod. Now, data node pods store the file data on the local disks of cluster nodes using another Kubernetes construct called host path volumes. And as always, we support Kerberos interaction for secure HDFS because that's very common. So the secure HDFS support that was talked about earlier is also included in this with that node out there. So finally, the name node and data node, because they're daemon pods, they're very special pods. And daemon pods are special because they don't actually need virtual IP addresses because there's only one instance of each type on a given node. As such, there's no need to worry about port collisions, and so they don't need to get a virtual network interface. So in essence, these daemon pods all have a physical IP address associated to them, which is kind of important when we talk about data locality right now. So what is data locality? The main idea is to send data to send compute to where the data is. So your Spark job has many different tasks. Each task wants a particular slice of it called a partition, right? So you want to send these tasks to where those partitions are. Now, because reading data over the network can be slow if your network is slow, reading the partition data straight from the local disk might be much faster. Now, Spark has source code that interacts with data locality. However, but this data locality layer was initially broken in Spark and Kubernetes and was broken in many levels. Now let's take a look at where it was fixed. So the first thing we're looking at is when a particular node has a partition of a task, we want to send the task to the exact node. Now this is data node locality. Now, if Spark wants to read, for example, file A and file B on HDFS, file A is on node A and file B is on node B, we want the Spark driver to be smart enough to send the task for reading file A to executor 1 on node A, where file A is, and send another task for reading file B to executor 2 on node B. Now, tasks will go there and read data from local disk with the help of local data node daemons. Now, how will the Spark driver as a software figure all this out? So the driver has source code, which checks if the file locations match executor locations. So here we compare file A location and executor 1 location. They're supposed to match for the file A location. However, the driver will ask the name node which data node is in charge of this. And it'll say the associated IP address of that node A. Now, the problem is that then the driver will find the IP address of the host. And here's a problem. It's an unexpected IP address. So as such, the Spark driver, in Yarn or Mesos, the IP would just be the same physical IP. Because once again, you're running this virtual network interface with virtual pod IP addresses, this is a problem. So the fix is simple. So you don't stop after getting the executed pod IP. You also ask the Kubernetes API to find the cluster node that the executor pod is running on. And then Kubernetes itself will say that it's node A, and we get the same IP address. And that's how you fix node locality. So similarly, sometimes node locality is not available, but rack locality is. When you build a data center, you put tens of servers in a single rack, for example, and you want to put a network switch on top of the racks that connects all the servers together in a rack. So the servers in the same rack can talk to each other pretty fast. Well, not as fast as node locality, but pretty decent. And so talking to servers in other racks may be much slower. You want to avoid that as much as possible. So here you have rack 1 and rack 2, node A and node B. And similarly as before, the situation is that you want to communicate in this direction. And you want to avoid, for example, the data node reading across the rack. And as such, to do that, you're going to be checking the rack locality. And as you can see, once again, because of the virtual network interface, you need to communicate with the Kubernetes client to be able to solve that, to be able to get the correct location. So in some cases, your data set's small. And for example, some nodes might not have enough space to be able to hold and you want to have like all your files, for example, stored on a single node. You want to use something like node affinity to be able to have all your executor pods running with local disk reads to file A and file B, which can be stored on the same node. That was also supported and then included by the Kubernetes scheduler. So with this fix of data locality, does this actually make a difference? So let's take a look at an experiment. So here's an example that Pepperdata ran, where we ran the same Spark job twice, which is a terasort. And as you can see, if you look at the durations, it's clear that the second run finished much earlier, 10 minutes versus 25 minutes. And it got faster because it increased the local disk reads a lot, which is the blue line, while avoiding the slow network reads, which is the orange line. And this is thanks to data locality. So it did make a difference. So sorry, I had to skip through the last parts because we have like a minute left. I want to get to some questions. But thank you guys for staying and listening to my talk.
We've got time for one question. If anybody wants to. All right, right here.
Hi. You put a lot of effort into getting Kerberos to work. Did you consider using TLS? And there's a patch in Apache Hadoop on using TLS for HDFS, and maybe just moving native TLS for Kubernetes with HDFS.
We didn't look into that as much, mostly because no, yeah, no. Most of our business use cases were around specifically handling like, that's interesting. Yeah, I understand. No, we didn't look into TLS specifically as an option. I don't think it was applicable in our use case.
All right. We have a coffee break for 30 minutes. Let's thank Ilan.